So last time we're continuing with sequential logic, right? Then as we are going towards sequential logic, then it's actually go a little bit beyond sequential logic. We're starting to consider the building blocks of a computer. Then you can say it's a sequential. It's a combination. It's sequential, or it's more towards architecture level design of a computer. So those are some basic components. We have talked about counter. Then if we go forward, we talk more about memory arrays. Now for memory arrays, we have a general design with an array that has input is the address. If we want to read it, the input is address, output is the data. Now if we want to write it, we have both address and the data as input, and there's no output for write transactions. Then with a memory array, we have the depth of the array and the width of the array. That's the width is how large is a unit. So for register files is typically 4 bytes. For caches is typically 32 bytes or 64 bytes or 128 bytes. It depends on what's your granularity of reading the data. Depth is how large your storage is. Now you can store a lot of data or only a little bit of data. It depends on the die size that you can support. Then we talk about the organization of the design, or the organization of general memory array. So we consider a memory array is listed in this way. So we have a word line and a bit line. Now the bit line represents the number of bit line represents how many bits are there in one unit, or this is the width, right? Now the number of word line determines the depth of this memory array. Then so basically, if we have more bit lines, we have larger bandwidth of getting data out of this memory array. Okay, if we consider one cycle per piece of data. Then after that, we talk about bit cells. What is a bit cell? Then bit cell is the circuit that stores one bit of data. So we store 1 bit of data at a cross line of a word line and a bit line. So it can store one bit of data. When we want to read the data, we first set the word line from 0 to 1 to enable this bit to be read. And if we set the word line to be 1, it's actually broadcasting to all the bit cells. So all the bit cells is enabled, then their data will be, their voltage will pass to the bit line. Then if we sense the bit line, we know what's the output, if the output is 0 or 1, right? So for the write process, we first set the bit line from the high resistant state to the store value, either 0 or 1. Now when we enter the word line, we actually because the voltage on the bit line is stronger than what is actually being stored there, then you can consider the voltage just flow into the storage unit and it's being stored there. Okay. Although if you look at the circuit, we can understand this better. So there are different type of memory cells and different technology to create these cells, and it's always a trade-off between how fast that we can access this data and how much data that we can store. And if there's a technology that can say it's the best, now I guess everyone would use that type of technology. But because they have different properties, they have different advantages, so at different places we use different type of technology to build a memory array. For example, the most common or the largest one is DRAM. DRAM stands for Dynamic Random Access Memory. Now when we say random access memory, RAM, on the other side is ROM, is read-only memory. So when we say read random access or memory, especially the access part, means we can both read and write data. Read-only means we only read the data, right? access memory means we both read and write data. Now what is random access memory means we can read wherever we want. There is no order, right? So what is the other side of random memory? What is an example of a memory that is not random? Serial or sequential. What is a sequential memory? Any example? Tape, yes. So tape is definitely one of the most important sequential memory. So it's a memory that you very likely you read only towards one direction. If in theory you can jump to another location, but it will take a very, very long time if you don't read in a sequential way. Okay, so tape is very good for backup, but it's not very good for random access. Now here the dynamic is on this other side. Dynamic is on the other side of static, as later on we will see static. Dynamic means the data will disappear if we don't keep writing into the stored bit, the bit cell. So as you can see from this circuit, it's as simple as a capacitor and one transistor, and one capacitor and one transistor can actually be implemented with one transistor. Then, so when storing one, the capacitor is simply storing charge on this side. On the other side, it's always negative charge. On this side is the positive charge. Okay, so then if we look at this, and then today we have more time to look at this circuit and try to understand how it works. It's basically a transistor, right? Remember, when we talk about transistor kind of works as a switch. So if it's one, if the word line is 1, that means this part of circuit is connected. If it's 0, that means this part of circuit is not connected. So when word line is 0, that means it's not connected, the data stores there and it's not going anywhere, right? Then when word line becomes 1, it's connected, then the charge will flow. Let's consider if the bit line has no no strong voltage to read or write, then you will actually have the charge is flowing out of this store bit, right? Now, since there's a charge that's flowing outside this, flowing out of this capacitor, then we can have an amplifier at the end, and then we can sense if there's a current or not. If there's a current, then we know it's 1. If there's no current, we think it's 0. Okay, that's how it works. Now, as you may realize, since this is a capacitor, reading the data is destroying the data, right? So that means for every read, right after the read, we have to write the same data again into it. Now, to write the data, that means we first set the bit line to a higher voltage or lower voltage. Now, if it's higher voltage, then we set the word line to 1. Then this one is connected. This transistor is connected. Then the high voltage will charge the capacitor to set it to 1. Right? Now, if the bit line has no high voltage and is draining the charge, then even it's charged a little bit initial data, the data will drain from here. Then it will become 0. Okay, that's how we read 1 and 0 in this case. And another problem with this capacitor-based design is charges on the capacitor will always lose on its own. It's not the battery, so it will lose charge pretty quick. And actually, there are not a lot of charge on there. So they want to save energy because every time you read the data, you don't want a huge current that goes through this wire, right? You only need the smallest possible charge to go through this wire. So they want to save energy, so they want to reduce the charge that is stored there. So there's always a trade-off, right? The fewer charges that is available on the capacitor, the more energy saving, but it's more likely that you will lose some data. So you need to refresh more often. So it may end up wasting more energy. But on the other side, if you put a lot of charge on here, on one side you probably increase the die size. On the other side, you may actually waste more energy you may actually waste more energy when reading or writing the data. So in theory, for this type of DRAM, you need to refresh it every a few hundreds. It's shorter than that. It's a few hundred millisecond to a few hundred microsecond to millisecond level. You need to refresh it. So refresh is pretty quick, and it can be done rather in a rather parallel way. So you can, it's basically a write. Then you really write the data in, then you write the data into this stored bit. Then it's refreshed. The charge is getting back to original value. Okay, and by the time when you are doing this type of refreshing, you cannot really read the data or write the data. But typically in your DRAM, I don't know if you have seen the DRAM that is available on the market that is for the PCIe board. No, not really a PCIe, but for your motherboard, you plug into the motherboard that have DRAM. There are actually many chips on it, right? So they're typically often carefully scheduled so that one chip is refreshing, the other chip is not refreshing. So other part of calculation can somehow continue going on to prevent a global hiccup that, like if it's really having some hiccup, even you move your mouse, you will feel that it's actually not moving. Right? So it's not, if you click something, sometimes it will not respond to your user interaction, which is not tolerable for a computer system. So this DRAM, and later on we'll have dedicated lectures for DRAM, is very complex, and it's much more complex than this. And there are many different ways to make it read and write data fast. So we'll talk about that later. But for the other type of memory is SRAM. Then SRAM stands for static read random access memory. So if you consider this one, the bit cell here, we say this is a sourceless bit cell. So it's not connecting to any power. It's not connecting to power. It's only holding charges, right? So it's VCC, the power source, 5 volt, or it really depends on what your specification, 12 volts or just 2.5 volts. It's actually not connecting to here, not directly providing energy to this. It's not holding that charge there. So it's sourceless bit cell. But if you look at here, how an inverter is implemented. Remember how an inverter is implemented? Let me draw it here. So if this is the VCC, if it is 5 volt, right? So we have one transistor and another transistor. And they are both connecting to the input, and this side is connecting to the output. And here is ground. There's 0 volt, and this is 5 volt, right? So this is how an inverter is built. Now here, we only need 2 inverters to connect to each other. So this type of design, this type of cell has sources directly connecting it. Because the source, the power source is directly connecting it to it, it actually will hold this value forever. It will not lose charge. Because the power, if it's lose charge here, the power will give it a little bit more, right? So it will not lose charge, the data will stay there, so you don't need to refresh it. That's why we call it static. It's always the same value unless you read or write the data. Okay. Then remember when we talk about SR latch. SR latch are designed with 2 XOR gate, right? So quickly help you remember SR latch. SR latch works in this way. It's another not XOR gate, NOR gate. Then which side is S? This is S, this is R. This is Q, and this is Q bar, Q prime or Q bar. Right? This is a SR latch. Then, So SR large are basically, remember, if both S and R are 0, if R is 0, then S is 0. So that means this OR gate will not consider the value from S and R, right? In this case, if S is 0, this is an OR gate, right? So an OR gate, let's say, if this is S, this is Q, right? We know S equals to 0. Then we write this as O, okay. If S is 0, O will always equals to Q, right? This is an OR gate. If S equals 0, O will always equal to Q. When Q is 1, O is 1. When Q is 0, S is 0, right? So that means when S and R are both 0, that means in this case, the word line is not selected. It's not connecting to anything. So they have no voltage. In that case, it's equivalent to this. Okay. When S and R are both 0, this SR latch is equivalent to this one. Okay. So that means, you know, SR latch will hold the data forever, right? The data will stay there. So when these two transistors on the word line are not connected, it's pretty much an SR latch there. So the data will stay there. Then, so if we have the word line enabled, then these circuits are connected. In that case, you can consider the S and R and Q prime are actually being reused by the bit line. So the bit line can be both the input lines and the output lines of an SR latch. Okay, so it really depends on if you're writing it into it or reading it into it. It's the power that is good enough to drive these transistors. So let's say if we already have a bit line that has this one, that side is 0, and there's a power source driving it. Then when we enable the bit line, they are more like the S and the R side. So they're writing into the latch. Okay, then the data will stay there. Now, if the bit line and the negative bit line is not connecting to source and it's connected to a sensor that sense the voltage, then they're more like Q and Q prime output. Okay, that's really some low-level physics or like electrical engineering design to determine why it's positive or negative. For computer architecture, I think the most important lesson learned here is for this type of memory array, we only need 6 transistors to store 1 bit of data. Okay, so 6 transistors means it's 6 times more die size compared to DRAM. But the advantage is we can read the data and write data much faster. If this is a small array, we can read and write data in 1 cycle or 2 cycles, no problem. Okay, so that's why for most of computers, I'm pretty much sure all of you have heard of L1 cache, L2 cache, right? So L1 cache and L2 caches are most likely implemented by SRAM. Then DRAM, that's 16 gigabytes of memory on my MacBook Pro, 32 gigabytes or 8 gigabytes, those are DRAM. Okay. So I can also provide you data. Have you heard of Cerebras company? So Cerebras is a company that produces a chip that called wafer scale chip. Still remember what is a wafer? wafer is a single piece of silicon, right? So as much as 16 or 20 inches. So how large is basically slightly smaller than the MacBook Pro screen, right? It's basically one. This is 14-inch, right? So its shape is different. So probably basically the same size as a MacBook Pro screen. This is a diagonal size, and that's a diameter, and there are some parts that it needs to be trimmed off. So basically the same size as a screen. So they sell the whole wafer as one product, as one chip, right? So how large is the largest chip? Remember we say is basically for NVIDIA GPUs 800 millimeter square is the largest one. But this one is probably like tens of times, not really 100 times larger than this one, but can hold at least 40, 80, these type of chips. Now, how large is the memory on a wafer scale chip? And I can tell you, on wafer scale chip, they only use SRAM. Now, in their second generation, the actual size is they have 80 gigabytes of SRAM. Okay, so for NVIDIA, H100, how large is their memory? Then basically there are two versions. One is 40. I don't know H100 if H100 has 40 gigabytes, but A100 has two versions, 40 gigabytes and 80 gigabytes. Okay. This is DRAM. And that's the size comparison between SRAM and the DRAM. And I also, don't get the confusion here. This 80 gigabyte of DRAM is not on this 800 of millimeter square, okay? So on a GPU, when you buy a GPU, you typically see something like this, right? This is a card. There's a fan, right? And there's a PCIe connector, right? This is a typical GPU. Now, if you take off the shell and take off the shell and the fan, you will see a PCB. Then there are a lot of like capacitors, resistors on it, right? So you will see the largest thing here is the chip, the 800 millimeter square chip. Now you will see many things on the side. Right, you see something like this, or two sides or four sides. Those are DRAM. Okay, so but still the size, the scale of this H100 or NVIDIA GPU is much smaller than this one. But because of SRAM, they definitely want larger memory, but they cannot. They can only hold 80 gigabytes of SRAM on a whole wafer. Now for L1 caches for GPUs is typically only hundreds of kilobytes, not even megabyte size. To L2 cache is several megabytes size. So for SRAM, I don't see anything can go to gigabyte level today. It's a comparison between SRAM and the DRAM. And also SRAM spends much more energy than DRAM. But the advantage is way faster, right? So for when we talk about cache, we always have this type of understanding. For a typical CPU understanding, is L1 cache. How many cycles we need to access? Let's start from register. Register is part of the core. The register typically we consider as one cycle. Okay. L1 cache for CPU understanding, then for GPU is totally different style. Now we typically consider is smaller than 5 cycles. Okay. Now for L2 cache is also SRAM, larger, but needs more memory transfer, like data transfer on a network. We typically consider it as tens of cycles. Okay, 20 cycles, 40 cycles, that's reasonable. So general understanding. Then we go to L3 or DRAM. When you write something like A equals C plus B, okay. When you write this type of line in your C or C++ code, what is actually happening is you're loading one piece of data from DRAM. You're loading another piece of data from DRAM. You're writing into the DRAM. Okay? It's a read, and write, and add operation here. So how many cycles is a DRAM? We typically consider it as several hundreds of cycles. If it's 1,000, it's still reasonable. Okay, it's a long latency. It's probably not very well designed system or highly congested system. 1,000 cycles is not super strange. Then if you go to hard drive or to another machine, then it's typically thousands or tens of thousand cycles. It's also reasonable. Okay, so you can see if we use 100 cycle to go to a DRAM, 100 cycle to go to a DRAM, and 100 cycle to write back, and to only spend one cycle in the add operation, right? So what's the utilization is 0.3% utilization, which is terribly bad. So that's why we cannot really only rely on DRAM as the memory. We have to have SRAM, but SRAM is too small. We cannot have gigabytes of size of SRAM. So that's why we find a trade-off. We put more likely to access data in SRAM, and we put less likely to write data in DRAM. So it's a trade-off between latency and capacity. Okay, so that's why there's no single good technology to solve a memory problem. And still, the memory access latency is still a big problem for today's computer. Then we talk about register file. The register file is more likely to be part of the core design. The register file, we're not only starting to talk about capacity and latency. We start to consider parallelism or concurrency. So we cannot only read one piece of data from a register file. We wanted to provide data as soon as possible, and so that multiple reads and write can happen at the same time. So for example, this register file has multiple ports for read and write. How many ports for read? There are 2 read ports, right? So A1 is connecting to RD1, and address 2, A2 is connecting to RD2, right? So A1 is connecting, if A1 has one input, then RD1 will get the output next cycle. Now A2 and RD2, now A3 is for write. Now we can write the data, then we put the WD3 on this side so that so you can consider everything on this side is input, everything on this side is write put, right? We put in input, then A3 and write 3, then we write the data into this register file. So we have this register file, and we have this 2 input and 1 out, sorry, 2 read port and 1 write port. Why we design in this way, and why we need 2 read and 1 write? Is that a reasonable combination? Then, yeah, you're basically right. You read more than you write. Consider for most of the instructions for your computer. It's more like you do sum, subtract, multiplication, division. In this case, you need 2 input and 1 output. Right? In this case, you can complete the whole thing within 1 cycle. Although, actually, when we talk about pipeline execution, in 1 cycle, we probably were writing something from before, from the previous instructions. Now later on, when we read the data, we read for a later instruction, and it will pass a few stages to calculate a result. And then the result will go back to the write stage. Now we'll write the data into the register file. It's a later time, but overall we want a 2-to-1 ratio for read and write. It's a typical consideration for register file design. So it's really this is how a microarchitecture design. So microarchitecture determines how our circuits are designed. Now when we say architecture or instruction set architecture, it depends on what our instructions look like. If most of our instructions look like this way, we have two read and 1 write. But if most of our instructions say we have a carry bit, right? For a comparison, well, comparison is probably okay. For some instructions, we have 2 in, 2 out. In that case, it's better to design register file with 2 write port. Okay, so this is how the instruction set may determine the microarchitecture design. Although, even if you have this type of design, can you support a 2 in, 2 out architecture? Yes, it's just a performance issue, right? There's always high-end chips and low-end chips, and energy, like some cost the lower energy but takes longer time to execute. It's always a trade-off. So the question is how this type of multi-banked register file are designed. Multi-ports register file are designed. So here we introduce 3 different designs. And when we're dealing with register files, we typically want it to be as fast as possible, and die size is not our first priority. In this case, we can select to use flip-flops. Now remember, when you say flip-flops, is 20 plus 20 something transistors, right? DRAM is 1 transistor per bit. SRAM is 6 transistor per bit. Flip-flop is about 20 transistor per bit. So we use a flip-flop here. So in this case, we have 4 flip-flops to store 4 bits of data. And if you want to have larger storage, just provide more flip-flops there, right? And then for input, the address is directly connected to a decoder, as we introduced in the general design of a memory array. We connect to a decoder, so this part will light up, right? Say if we're selecting this serves as the word line, so this serves as word line. So this one will light up this one. Okay, this is write part. Let's look at read part first. So this register will always generating data. To here, to the output. And A1 is selecting the generated data from all 4 registers. Then it's just one of them will be routed to RD1. Then at the same time, some other one other line, or even the same line, can be connected to RD2. In that case, we can read the same register twice within the same cycle. It's totally possible. Okay, so basically the read part is selected by a multiplexer. It's basically just consider we want to directly connect the flip-flops or registers to the output. But we need to, since we only have 1 output line, but we have so many register lines, so we have to use a multiplexer to select which one is the one we want to use. Okay, so same thing with A2. Then on the other side, we have the write logic. Then the write logic is basically the write channel is always connected to here, right, to a multiplexer. Or let's start from here. And say, if we don't want to write it, what happens is basically the next cycle, the data will stay the same. So we want it to loop back. So in the next cycle, the data loops back, so we're writing the same data back to the register. Actually, since the transistors are not flipping, we're not spending a lot of energy to keep the data being stored in this register. But if we want to write the data, here we have a selector, right? We have a selector. We select, say, do we want to use the write data or the original data? And if this is 1, we use the write data, then this one, the write data goes into the register. Otherwise, the original data goes to the register. It's only enabled, the write data is only enabled when we want to write something, right? If it's, say, we can have something like a write enable bit. So when this write is not enabled, we keep the data the same. We don't do anything. Okay, this circuit is a little bit complex, but you can just parse it as 3 parts. The read logic, the store logic, right? The loop back is the store logic, and the write logic. Okay. This is one way. So for CPUs, register file implemented in this way is generally okay. We're not that short in register. We're not that short in die size, and we really want extremely low latency to read registers. And for GPUs, when our data is a lot, we have a lot of register. The die size is scarce resources. It's limited, so we don't want to use flip-flops. We still want to use SRAM. So in this case, just consider this one as a SRAM 60 unit. Okay. In this case, we do this. We have multiple word lines and multiple read and write lines. Okay, these are bit lines. Those are word lines. Those are address input. Now we first have decoder, and decoder are connected to these lines. Just consider it's almost 3 independent input and output logic. Okay, so almost the 3 independent input and output logic. And when this one is generating data, then we go through some gate. So if this one is selected, then it goes onto this wire. And if this one is selected, it goes to this wire. So in theory here, we're basically using an AND gate to serve as a multiplexer to go to the read wire. Then on the write wire, it goes back to here. Then we don't have the loop back, just consider loop back is built into the register. Okay. So this is another way to design a register file. Save some space, then in general is still okay. Then even this type of design sometimes is too much for GPUs. So we're just using this as an intermediate step to go to our final step. That in actual GPUs, how the register file is implemented in a banked style. So they cannot really have so many wires that go through every cell. Right? It's a lot of wires. So instead, they find some trade-off. What they do is they do something like this. So they have banks. This banks is a single port register file. Now you can either read or write into a bank. Okay, so but we can have multiple banks. We can have multiple banks. And then basically when we want to read it, so if we want to have an address, we want to read it, we can either say, okay, shall we enable this bank to read one register? Now if we read the register, we go through this multiplexer and output the data from this RD1 line, right? Then if this one is selected, then we read another register, then it goes to RD2 line. Okay, but there's a cross line here, so because some data that we want to read from bank 2, but we actually want to read through the RD1 line, and sometimes we want to read data from here, but we want to read data actually from this port. So what is actually in this register bank 1 and what is actually in bank 2, you can consider in this way. For most of the hardware design, we will write, say, register 0 will go to bank 0. Okay, then register 1, we go to bank 1. And let's just say 2-bank system. Register 2 will go to bank 0 again. Then register 3 will go to bank 1, and so on. So this is a very common style in computer architecture, and this is called interleaving. Interleaving. So in interleaving, now we try to use a round-robin style. R0 go there, R1, R2, R3, R4, R5. Then in this way, we evenly distribute the registers to this 2-register file. So why we want to use this type of interleaving? Because more likely we're going to do something like R1 equals R1 plus R0. So these 2 registers are likely to come from 2 different register banks. And for most of GPUs, 2 banks are too small. Like they have 4 or 8 banks, or even more. Okay, they can have many different banks. It's really a parameter. The more die size, the more bank you have. Then in an extreme case, consider this one. If you consider each register has its own bank, this is the design. In this design, each register has its own bank, so we can read and write them at the same time. Okay. So because this wire is directly connected to each register. But in this case, then in the I don't have, if we only have one port, if we only have one port, that means we only have one bank, right? So there's 2 extremes. In this case, we have 2 banks. As you can see, the wires doesn't really need to go through all the cells. It only needs to connect to this bank. Then this bank will eventually select one piece of data as the output. Then this data will be routed through this multiplexer as the output. Okay, so if we want to read something like R0 and R1 in one cycle, yes, it's totally possible. Like we can have this A1 to read R0 and A2 to read R1, and they can output in the same cycle. But if we write something like, say, R1 equals to R3 plus R5, okay? If we have R3 plus R5, because R3 and R5 are actually coming from one bank, right? They come from this bank. If they come from the same bank, this bank is a single port bank. It's a single port register file. So it can only support read and write a single register at one time. So in this case, that is the term called serialized. Serialized means we can execute something in parallel, but for some constraints we have to execute one after another, and this is the term for serialized. In this case, we have to serialize these 2 read, and it takes 2 cycles to read these 2 registers. Okay, then it really requires this simple circuit with multiplexer cannot really handle this case. It requires more complex cases. But with sequential design, since we learned the finite state machine, I'm pretty much sure if you spend some time, probably a day or 2, then you can draw that type of circuit out, right? So don't consider too much detail, just consider, oh, that's something possible. Okay. So here, this is more like what happens in a GPU, that if you're lucky, you can get the register within one cycle. If you're not lucky, you may take 2 cycles to get your registers. Now it really depends on what registers you are reading. So if you're reading 2 registers that are actually coming from same bank, and your read have to be serialized, this is a terminology called bank conflict. Right? Because you have a conflict in the bank that want to read. The bank cannot serve 2 transactions at the same time. It have to wait a little bit to get another transaction register read completed. So it's a really design trade-off. If you want to have high performance, you want to have more banks. If you care more about the die size, you should have more banks. You should have fewer banks. Now, if you care about performance, you have more banks. And to one extreme, you can design something like this. Then this is like one register, one bank, right? So all concurrent to read and write. The best type of design, but definitely more die size, more wires, and more transistors. Okay, question?
Are all registers implemented with banks? Or are there like times where you wouldn't use a bank?
Say again?
So it's like this, like the bank system is like standard for like all types of registers, like on the CPU and the GPU. And
I would say CPU more likely to employ this type of design when the registers are not a lot. GPUs have much more registers than CPUs. So GPUs more likely to implement this style. So it can wait a little bit. GPUs are not latency sensitive, so it can wait a little bit. So bank conflict is typically not a super big problem for GPUs, but for CPUs, latency is very sensitive. But I wouldn't rule out some CPU want to use a banked design if they have a lot of registers.
GPU have maybe so many threads accessing the, and then all of a sudden they have so many conflicts. Why they still use this? Like you said, because the memory, the resources abundant, so they can design this way, but they actually have so many threads. And so many threads, they have so many registers to access. If it's like all access at the same time, and the conflict cannot be mitigated.
Okay, so I think most of you here need a little bit background in how GPU works, right? So to answer this question, so the question is, GPUs typically have bursts of register read. It's not bursts; it's the traffic going out of the register file are much larger, right? So how GPU works? GPU works in a way that is called SIMD. SIMD means if you have add R1, let's actually use V1. V1 equals V2 plus V3. Okay, I'm writing V because this is a vector register. When we're executing this instruction, we're actually executing 32 or 64. 32 for NVIDIA, 64 for AMD. We're actually executing that many threads. Right? So when we're reading from V2, we're actually reading from 32 registers. So although they both named as V2, but they're for 32 different threads. So we're reading 32 threads. In that case, because there are 32 threads, right? They have 32 sets of banks. So if they have if it's a 4-bank register, it's actually 4 multiplied by 32. They have actually 128 banks. Okay, so 128 banks, but you can either understand it as banks or it's a separate register file for each thread. because they will rarely like communicate. Right? Communicating data from one thread to another is relatively advanced instructions.
Basically, they have like a collapsed memory access is related to this, so they all interleaving in 32 band. So
Yeah.
basically, the collapsing this way, so the interleaving number, the module is 32.
So
the every 32.
So the interleaving. Yeah, I wouldn't say it's a interleaving system. It's complex. So you say, this is a register file for thread 1. This is a register file for thread 2. This is a register file for thread 3, right? Then within thread 1 and within each thread, you then have 4 banks. Okay, so you have one input. Let's say if this is R1, register 1, the address 1, right? Address 1, you only need one input. Then address 1 will go to all the ports, right? Eventually, you'll have 32 wires out. Then they're giving you different values, and each of them is 32 byte. Sorry, 32 bit, 4 byte. Each of them is 32 bit, and there are 32 of them, 32 wires. So in one cycle, you put in one address, it gets out of that amount of data. That's a GPU. That's within one core. And of course, it's a multi-bank, right? So you need a multi-ported. So you need a R2 to go in, so it will have another set of output. Okay, so this is how GPU register file works. So if you say these are banks, yeah, those are banks, no problem. If you say those are banks, but you consider those are separate register files, it's also okay. Okay.
So at the worst case,
Hmm.
How conflict will this be if they access that worst case?
So it's actually not that bad. Then if R1, if say R0 is here, V0 is here, V1 is here, V2 is here, V3 is here, right? Then V4 is here. If you read V0 and V4, so if R1 is V0, R2 is V4, you only need 2 cycles. Only need two cycles.
Something like a cache, it's a 4-way cache.
Yeah. Okay. Yeah. Let's continue. So on Tuesday, we're about 20 minutes left. We're at these slides. On Thursday, we still have 20 minutes left, and we're still on these slides. Okay, now read-only memory. So read-only memory is a memory that we can only read the data. So who write the data? The manufacturer will put the data in. So we almost never want to write data to this type of storage. However, I can tell you pure read-only data today almost doesn't exist, because your vendor, the manufacturer of the device, always want to change something for you. So typically you will consider something like firmware update or BIOS update. Those are something that you're actually writing into the read-only memory. So they write something that is most fundamental to your chip. Okay, so today we don't really use this type of technology. We actually use flash instead. So everything is flash, but this read-only memory concept is still there. So what is the original read-only memory is implemented? It's basically implemented in this way. So this is a decoder, right? So don't consider this data is connected to a ground level, to value 0. They're just wire connection. So if this side If we put this is to 1, and if this is connected, then the output will be 1. Then if it's not connected, since there's no one is providing the voltage, its value is 0. And on the other side, this value is also 0. Okay? So if this is 1, others must be all 0, so the output is 1, 1, 0. Okay? So as a very early stage read-only memory, so now on the spaceship that goes to the moon is actually using this hand-woven ROM. Okay? Then if you are curious about how it is done, it's actually there. Watch that video. That video is like 45 minutes long. It's actually very long to introduce how this is done. But basically is something that there's a magnet circuit, right? So there's another piece of circuit that is going through this magnet or metal. Now if this circuit gives the value, then it's actually the current to go through this circuit, then it becomes a magnet, right? It becomes a magnet. So when it becomes a magnet, so this is the word line, and there's another. This is the bit line. So bit line goes through this magnet, or it goes past this magnet. So if it's going through this magnet, whenever this magnet is enabled, we will detect the current on this wire, right? So in that case, this is a 1. If it's woven outside this metal circle, it cannot detect the change, so it's 0. So that's how this ROM works. So for Apollo machine, why they use this type of design is you consider by that time technology is limited, and you really need to prevent something like very vibrant shaking, right? High G force, and also cosmic rays that may have some bit flip. You really want something super reliable, and no matter what, you can still read data from there. So that's a ROM from Apollo machine. Yeah, these are some very basic explanation of this type of system, how it works. Then, so this is a read-only memory. But if you consider read-only memory, it actually can store some data without a transistor and can actually perform some operation without gate. So for example, if you consider this type of design and this design, they're actually equivalent, right? So if our input is some certain, let's say our input is 1, 0, we get this one is enabled is 1, and it's not connected, right? It's not connected to this line, so it's 1, 0, 0, right? So this is an OR gate, it's connected here. So if it's 1, it's enabled, so our output will be 1. And this line, the second wire, is not connected to the second gate, so it's 0. And this one is not connected to this wire, so it's also 0. So if our input is 1, 0, in this circuit, we output 1, 0, 0. In this case, we also output 1, 0, 0. So in this sense, a read-only memory is basically can be considered as a predetermined circuit, right? Or I can say it's a lookup table, right? It's something that I have the input, I always know what's the output. It's a certain lookup table. That comes to something called logic arrays. In logic arrays, how we can perform some logic with read-only memory. Then, if you consider this case, these two cases are identical because for certain input, we always get the same output for these two type of circuits. Then, but the problem with this design is we can only get OR gate, right? We can only have OR gate. We have no way to have AND gate. So how we can have AND gate there? If we know AND gate and OR gate plus NOT gate is good enough for any type of circuit, then we can actually just make it slightly more complex to build any type of logic. And how this is done is basically in this way. We provide the NOT value, right? And this line serves an AND array. So don't really think too much about how it's implemented. I will have a example later how it's implemented. But here, just consider if it's selected, then it's in this Boolean equation. Okay, so not A is selected, not B is selected, C is selected. So this represents A prime, B prime, C. Then A prime, B, C prime, and A, B, and X is or of the three min term, and Y is AB prime itself. Okay, so by using this type of design, then we can basically implement any type of logic. And how it can be implemented with a circuit is in this way. Okay, see if you can understand this. So here, this is a, you can consider this is a power, right? This is a gate. So this gate is controlled by A. If it's controlled by A, then if A is 1, then the power will drain to 0. Then if A is 1, then the whole thing is 0. A prime B C is 0, right? If A is 1, this transistor is connected. If it's connected, the high voltage will go through this gate, then will disappear. So will not go towards this direction. So only if B is not connected, C prime is not connected, we can have high voltage pass to this OR gate. That's how we implement the AND gate. We actually have these transistors connecting to the other side of the not connected part of this wire, this signal. Okay, in this case we have AND gate implemented. Now OR gate is easy. Now if it's connected, then we do not select it. The power will drain from here. Then eventually we have a NOT, we invert it, and we get our OR result. Okay, that's how we implement this type of circuit with transistors. It's actually very simple. Without gate, we can support some logic. Then, so I think you must heard of something called FPGA, right? So how FPGA is done is basically by using lookup table. So if you want to implement some logic, you will write a piece of code in Verilog or VHDL. Verilog or VHDL are languages that's for hardware design. It describes what type of logic that you want to perform. For example, you want to have two values added together. Then, in this case, a software will actually generate the truth table for all possible input and generate this type of lookup tables or this type of simple logic arrays for you. But these simple logic arrays are only for combinational logic, right? So what FPGA is doing more than this type of simple combinational logic is by combining different lookup tables together with registers, so it can also support sequential logic. And today, FPGA is getting much more complex than the early days FPGA. For example, FPGAs will equip the multiplier. You don't want to use a lookup table to multiply a data, right? Otherwise, there are too many possible inputs. Like multiply two floating points data, 32-bit input, 32-bit output. There's too many combinations, right? It's 2 to the power of 64. Right? That's too many combinations. It cannot be achieved with this. So FPGAs today equipped with multipliers. So it has more and more different type of logic built in with an FPGA, but it's still, you can write something like a Verilog code and to use FPGA to generate this type of lookup table and to produce the result for you. That is something that people typically use before they produce a real chip. They implement the chip in Verilog code, and they burn it into FPGA. Then the FPGA will run the same logic, and if you can test if the logic is correct or not. Then also FPGA, because it's pretty much lookout table, it doesn't really need a lot of cycles to generate the result. It's considered to have lower latency than real circuit, than CPUs and GPUs. So FPGAs today is still useful, but only in some cases. And high-end FPGAs are actually much more expensive than CPUs and GPUs. So it really depends on if it fits your need or not. Okay, so as a summary, we're finally done with the sequential logic, and also pretty much these 5 lectures is the whole digital design course for undergraduate level course. Okay, at least my undergraduate level course of digital design only ends about at this time. So we'll talk about sequential logic, we talk about finite state machines, how to use finite state machines to design a circuit, and for something like even for some code pattern detector, right? So consider in some games, if you type a password, then it will enable a feature, and in that case you don't even have a text box for you to input password. How it's enabled? It's pretty much state machine. Then you learn the state machine how to detect the code pattern, like a pattern, right, with a circle of state. Then you can eventually get to the unlock state. Whenever you get the unlock state, you unlock that feature. So even I think it's super helpful for you to implement software. Then the building blocks, we only introduced the counter, but there can be other building blocks. Now we will talk about them when we are in design CPU cores. Now we talk about memory arrays, SRAM, DRAM, and RAM with their advantages and different advantages, disadvantages. The logic array, we talk about RAM as a program logic array and FPGAs. Okay, so those are some fundamental elements for digital circuit. And at this stage, we're probably not going to draw gates at this point. We'll probably at most will draw multiplexer for selecting signal. But for the basic things, when we talk about, say, okay, here we need a multiplexer, don't think how it can be implemented. Just think it's possible that someone spent some time and it can be implemented. Okay, then we'll start from there to build some more complex circuit from there. Then in the next 2 lectures next week, we're going to deviate a little bit from architecture, from circuit. We're going to talk about how to run simulations, how to write simulations. So especially I'm going to introduce the Akita simulator framework, that is the simulator framework developed by me when I was an undergraduate PhD student. So I still think it's very useful. So I'll teach about that. For the next assignment, at least next formal assignment, you will understand why I'm saying next formal assignment, because we'll have an informal assignment. Next formal assignment, we'll write some simulator code to start to simulate sequential logic. Then simulate instructions, simulate cores. Eventually, hopefully, everyone can simulate a simple rectifier core and can execute some simple programs. Okay, that's the goal for the rest of the semester. Okay, that's all for today's lecture.